All right, everybody. Thank you for your time and attention today. This is the Extended Reliability Assessment for Electronic Components, Phase 1, our end of project report out. We have several members of the team here today, and our primary presenter is going to be Stephen Dunford from SLB. We do have another session this evening at 11 p.m. Eastern Time, if you'd like to hear it again. But we are recording this session, and we will make the recording and the presentation that we're giving available to all of the folks that registered. We'll send out an email to you probably early next week once we have all of that ready to go and posted. We also do have an end of project report that is available and is posted already on our project page. I will put that link in the chat window so that you have access to that. I do want to let everybody know that you are on mute, and if you do have any questions during the session, that you would please use the chat window and I will gather those and ask them at the end. If the lines aren't too noisy, I will try to unmute people and let you ask your questions, but it looks like we have a fairly large crowd, relatively speaking, so it may end up being smoother if I ask the questions from your chats. So with that, I want to thank you again for your attention, and I'm going to turn it over to Stephen.
Thank you, Mark. Well, we welcome all of you to our presentation. For the agenda, we'll move to the next slide. We'll talk a little bit about the project team and why we put this together, some of the background and what we're hoping to accomplish through the experimental methodology, and we'll talk more about what we've concluded from these last few months, our work together, and then we'll have it open for questions. Next. This is a list of the main contributors. We have a broad spectrum from the electronics industry, from consumer electronics to critical fail-safe industrial applications. And all of us are interested in several things. One of them is in extending the reliability of electronic components, obviously from the title. We want our products to last longer, but we also want to meet the new sustainability goals that we're implementing. Next slide, please. So part of the background or the driving force that we have here is we do want to reduce the amount of electronics waste. It's becoming more and more of a problem. We'd like to lower our carbon footprints, and this has helped to increase the interest in extending the life of the electronic assemblies from many different perspectives. So from consumers and governments, we see consumers are wanting their products to last longer for various economic reasons. Governments are also recognizing the opportunity and benefits of reducing the electronic waste. And the resulting public opinion is leading to increased government regulations. And these are also contributing to the need to extend our reliability and lifetime of products. In recent years, we've also faced the supply chain issues with increased demand and inflationary replacement costs contributing to this effort as well. And so we're looking for opportunities to extend the lifetime of the components. We also show that the service time and the service expenses of critical expensive equipment, the downtime is often something that we would like to avoid. So in this extended reliability assessments, we're trying to identify and select components that are suitable to be refurbished, reused, or reassembled. That's part of the discussion. The components could enable longer usage beyond the initially assessed shelf life and the expected operational life. And if we'll go to the next slide, please. So this is the typical bathtub curve, and due to cycle time and market pressures, the components are usually tested to ensure the elimination of infant failures and provide a reasonable estimation of the useful life. The end of life or wear out is rarely determined by the qualification testing done at the manufacturers. And plus the useful life will depend on the application conditions, and that limits the effectiveness of some of the manufacturers' testing, because in actual testing it is the conditions may be severely different. So the high value repair in many cases may exceed the replacement costs, and assemblies are scrapped at first failures before they reach their optimal lifetime. And because we don't know and from that, we don't really know what the remaining useful life is of many of these components. Next slide, please. So in our objective, we want to define a method or methods for selecting existing electronic components that can have extended reliability. We want to look at the standards and establish new standards if possible, and a database of extended reliability components. What makes them, what are the properties of these components that make them fall into this category for extended reliability? In the scope of the project, we were looking at part selection methodologies to study components of particular families. We were hoping to establish a common test methods and stress conditions to assess the materials and the components, and identify methods to prolong or extend component lifetimes to mitigate the typical failure mechanisms. Now, we understand that there's a lot of test methods out there that have been used for decades and are quite effective, but we're also looking to determine if there's something that we can do to speed these up. So in the component selection, next slide, please. We're trying to do several things. We want to look at the environmental conditions for various applications and categories. We're looking at new off-the-shelf passive and active components. We're considering board level testing versus testing of individual components, non-assembled. And but the emphasis will be on the first level interconnection, and we want to emphasize that we're not wanting to do a solder level test or a second level connection test. There's plenty of those that are going on right now, and we're interested in what happens with the components themselves. So in the first round, we're limited to, or we're talking about limiting to a particular family of components that would be easy for us to work with. So we've considered SOICs, DIPs, Gullwing SMT packages, but we're also interested in understanding the ease of functional testing so that we can not just identify the issues with the materials, but we want to know when we begin to see variations in the functions. Next. So we're looking at the typical thermal cycling tests, but in that we wanted to point out that in those tests, it can really extend the amount of time it takes to complete the test for thousands of cycles. And in this slide, we show some examples with QFIN packages up to 3,000, and I've seen a few more beyond that. BGAs, depending on the test conditions, 8,000 cycles. And other gull wing leaded components, we've seen data up to 10,000 cycles. And what we would like to do is we'd like to minimize the time, if at all possible, that this is taking, but still have failure mechanisms that coincide with the failure mechanisms we see from actual applications. So we're looking at, can we improve current tests to increase accuracy in predicting the failure mechanisms, or produce better component lifetime predictions from that? We're asking questions about, is there a method to assess the actual component lifetime more quickly? With the existing tests that we have we really exhausted all the possibilities or potential modifications that could be made to these tests to give us a better prediction in a shorter amount of time? Next. Obviously, in our discussions, we've pointed out that modeling and simulation will be very important to establishing the initial test parameters and identifying areas that will have higher stresses that we will be monitoring. So this is just a slide to highlight that. Go to the next slide. And this is an example. It's an examination of standalone versus board level stress, and where the highest stresses will be located. But in this particular comparison, it shows that a standalone component is actually going through higher stresses. That will vary depending on the environmental conditions. And but again, it's an example that we can gain a tremendous amount of information to pinpoint our analyses by using modeling and simulation. So if we look at these environmental stresses, we're looking at the temperature and atmospheric conditions. The thermal stresses induce warpage, bond wire liftoff, and shearing. There's polymer degradation and changes to the material properties. We know that the TG, the modulus, the adhesion strength, and sometimes or will be modified as due to the temperatures. Also, there can be ionic contaminant migration, such as chlorine, and the electronic functionality changes over time. And we know that again, with the amount of temperature, we often derate components because we know we're not going to get the same functionality at extreme conditions. And because these extreme conditions can accelerate the degradation, we have looked at different environmental conditions. In the next slide, we show a list of typical environmental test conditions that are used for different applications. Because we have a interest from a wide variety of industries, we would select particular temperature cycles. I don't think we can do all of them, but we would select those that we think would have the most applicability. and apply those and to evaluate the reliability in those conditions with the opportunity to take the results and apply it to other conditions. We go to the next slide. We also know that there are a number of other environmental conditions that we have to consider because they also accelerate the degradation. Certainly moisture ingress, mechanical vibrant shock. We know that depending on the electrical currents that we can see modifications in our components and in the buildup of intermetallics, for example. The chemical interactions that the components are exposed to, and possibly even potential radiation effects can induce these failures. And those are all considerations as we move forward. We'll evaluate the effects on individual materials in these components, and we'll gather as much information that's going to be detailed information about these components as possible so that we can evaluate their effects on the reliability of the components as they degrade over time. And hopefully we can identify those materials that give us an increased reliability of the components. Next, please. Part of what we'll have to do also, if we're going to, as we do the board level testing, we'll have to design the PCB because it can play a critical role in the reliability. And the team will need to finalize and agree upon the design. Modeling and simulation will be important to help predict the potential effects of the PCB on the component reliability. So this chart lists many of the different variables that we will have to consider from the component, the PCB, and the assembly. Please. So when we consider the PWB or the PCB, as we've gone through our discussions, several things have come out. We've felt like we need to have a high TG material, and this will help both in low and high temp applications. So for example, high TG FR4s, and but as we go to higher temperatures, if we select to go to the higher temperatures, we'll have to consider using other higher temperature resin systems, such as some of the polyimide materials that are there. We'll also need to consider the surface finish, the layer count, and we'll need to have a solder mask that will be able to endure the conditions that we plan to put them through. We don't want it coming off before we finish our tests. Again, because we're emphasizing the component and we don't want degradation of the circuit board to have a larger effect on the components than we had hoped. Next, please. Yes, I've already gone over this, a little ahead of myself. Let's go to the next. We, in looking at the different stress tests and the types of things that we are going to have to consider, we've made a list of the potential failure mechanisms. I don't think we need to go over this in great detail, but we wanted to list it to make sure that we are evaluating or considering all the different inputs that could be affecting the reliability of our components. Next, please. This is an example of a laptop evaluation that was done. And the team will be putting together a similar chart to identify the different tests that will be done for the particular components and the environmental conditions that are chosen. And then, of course, there will be the reliability predictions, calculations that will need to be done based on the results. Next. As we looked at the industry standards that are there and some of the things that are happening, we know that some of the AEC requirements are going to higher temperatures. And again, many of the test methods that have been out there for a long time, they may be used. We may take a different look at how they're used or evaluate whether or not that they can be accelerated. Because the circuit board materials and the encapsulants of many of these components are polymers, the oxidation and the effect of oxygen degradation on the components and the materials is a consideration. There's been a few papers that have published with the exposure to ozone, but we know that that's a possibility, and we've discussed that. Certainly other tests that are commonly used, such as the salt spray, the mixed flowing gas tests, flowers of sulfur, and so on. There may be a combination of these tests that will help us in the evaluation and possibly speed the evaluation, and that's also part of our discussions. Next slide, please. So in summary of the phase one, we have looked at this, and certainly we, in the option A, we want to be able to estimate or come out with an estimate for the lifetime of components. What is the degradation that occurs most rapidly? What are the things that we can do to mitigate those failures, to extend the lifetime of individual components? And this may be through a modification of the test methods, but we definitely want this to have application for the component lifetime in the conditions that they will be used in their application. Second, as we look at the test results, we may want to concentrate on particular failure mechanisms and propose mitigations for that. And there may be a test method that highlights those particular failure mechanisms that we can use, maybe stand alone with that test method to evaluate components. And third, we may modify those test methods that we might be able to demonstrate similar failure mechanisms to what we would see in the applications. If we can do this, we might be able to eliminate parts much faster. As OEMs, we can do comparisons between components from different manufacturers or different models, different batches and date codes. But we really want to also look at these methods for identifying robust materials. If there are materials or formulations that work better, we would encourage the industry to begin adopting those or developing similar components that would help to extend the lifetime of the components. Next, please. Of course, out of this, that was the intent of the first phase. And then as we look at phase 2 and begin starting a phase 2, the follow-on steps for phase 2 would require the team to develop these ideas in much greater detail, to put in details of which tests will be run, certainly the design of the test vehicles and the range of conditions that will be tested, whether it's harsh environments that would accelerate the degradation and be beneficial, or something that would be maybe testing may not require that harsh environment, but those conditions will be considered. Certainly, we have to finish the PWB design or PCB design and the materials that would be used for the low and high temp applications. The modeling and simulation needs to begin to be able to identify where the areas of concern would be for individual components. We've also, in phase 2, we want to consider different protective coatings that could be used to extend the component reliability, maybe reduce the polymer degradation, or slow it down. We do know that iNEMI is in the phase 3, or we're now starting phase 3 for a conformal code evaluation. And as we've looked at those, the publications that they've made there, they've been looking a lot at the corrosion effects on the metals. And so there may be some opportunity to benefit from the testing that they've already done and understanding the potential benefits as they relate to the polymers, but monitoring their testing and what they're doing will be important so that we can avoid duplications. Next slide, please. The second area, or the second result of this, was that there's also been an interest expressed in the use of recycled components. This would be a new project, and so we're also not only recruiting for phase 2 as described previously, but we're also looking for the potential of starting this new study and recruiting a team to put together a statement of work for evaluating the possibility of reusing high-value components. And so they would identify which components might be of greatest interest. These could be high value because of their cost or their criticality in particular applications, but also due to obsolescence and as we've experienced, the supply chain issues. We would identify and recommend the rework procedures that could be used. Hopefully they would not be too expensive. We would look at the high value components as far as the process of removal and rework, and possibly even pull components that have been in the field or been in an application for extended periods of time already and evaluate those to see how long they last after being placed on a new assembly. Of course, refurbishing would be refinishing. There may be some replating, reballing the BGAs, and possibly a coating of the components to extend their reliability. The team would need to do a poll to make sure that there's an industry interest or a market for this. And in the system, again, there would have to be accelerated aging to retest to ensure or provide data for what would happen to the components after, or how long the components would last after going through these processes. Next slide, please. So I'll turn it back over to Mark.
Yeah. Thank you, Stephen. Yeah, so that's a summary of the activity that the team did. I did post in the chat a link to the end of project paper, which is available, which goes into a lot of the things that Steve went through in 20 minutes in much more detail, which I hope you'll take the time to download and read. If you have any questions, I would say please put them in the chat window. I have one that's in there right now that came early on before we got into the slide about potential study of reused components. But I'll ask it to Stephen and Sue Chen here. They're asking about when one assembly is repaired, if you have removed components that you could classify as reusable or not reusable, would that change the repair method that you might use? And does iNEMI agree on that? And I'd say from an iNEMI agreement standpoint, we haven't done that project yet, so I don't know. But
I agree with the question. Yes, the removal or method is something that we would definitely need to be considered. There's a lot of process development that would need to be done there. We do, at least in my experience, I've seen that repair of an assembly can result in a lower lifetime of the repaired assembly. And so that would definitely be a consideration as to how the component's removed. If there's a process that is less stressful on the component, that's definitely going to be an advantage.
Seems the folks are agreeing with you.
Yeah, probably the project we might want to suggest the methods to remove the components. That is
So I
part
think
of the objective.
Mm-hmm.
Yep.
And that is, as I said, that project is in its early stages of what is it that's important. So these questions that you're asking and wanting answers to are what we need to find out so that we can focus that project appropriately. So if you're interested in more, providing some more feedback on that and anything else you've heard today, please email me, marques@inemi.org. It's up on the screen so that I can capture that. We do have some other questions here. So from Dennis, he says our project touches on work happening in many other organizations and mentions JEDEC, SAE, and defense, et cetera. Is iNEMI reaching out to other organizations for their experience?
Well, certainly that's part of what we're doing right now by telling the world what we've been talking about and asking for participation.
Yeah,
go ahead, Mark.
No, I was just saying we did evaluate a bunch of these standards that exist today as part of our early stages of the project. Just wanted to, I think, but that's only public information, not necessarily what they're currently working on. So yes, the phase 2 of this project would need to be continuing that engagement and or developing more of that engagement with these other organizations. Yes. We don't want to duplicate efforts. So if they're already going down the same path that we are, that's Let's see here. What else we got? I did drop the link to the paper in the chat again. If you joined later, apparently the chat doesn't have a history, so I dropped that in there. The presentation and the recording will be made available on the iNEMI website, and we'll send an email out when it's available. It should be next week to all the folks that have registered for these calls. So you'll get that. So a phase 2 related question here, which is interesting, I hadn't thought of it, is do you plan to buy the samples or ask manufacturers to supply them? And is there any thoughts on the differences between two ways?
Well, certainly any available components would be welcome. Cost is always a consideration in any effort that goes in, and if there are vendors that would supply components that have been through or maybe have been returned from the field, that would be an advantage. But certainly if we have a better understanding of what the exposure has been in those applications, the length of exposure, the locations where they are, any of that information would also be greatly appreciated. Other than that, we would have to purchase components and expose them to environmental conditions for a period of time before putting them on a board and then making comparisons to components that had not been exposed in those tests. Joe asks a really good question here about the issues with counterfeits. That's a problem, particularly with obsolete components or components that are hard to find. And with this, it is definitely something that would have to be considered, and how to identify these components that have been refurbished or reworked, so that we could avoid issues with the manufacturers and contaminating the supply chain in such a way, or causing confusion in the supply chain. But it's a very good point, Joe.
Yeah, if you're willing to talk a little bit more about that, Joe, I would drop me an email. I would love to have some more conversation on that, because that's something that both iNEMI is interested in, as well as other projects that I'm aware of that are starting to get into this space are also interested in. Such components are called as original fakes. Okay. Interesting. I had not heard that. Are there other comments or questions from anyone on the line?
Well, I hope we can come up with a more positive label for the components as this moves forward.
Yes. So, any questions from anyone else or comments that you'd like to make? Otherwise, I'll give you a few minutes of your day back.
Well, I would like to thank all the participants in phase 1. We had a good team, lots of good opinions based on the experience they've had in the different industries. A good learning experience, and hope we can continue and add additional members to the team.
Yes, absolutely. It's a very big, I think, objective that the team had, and lots of diverse applications that we have to discuss. So I look forward to seeing the phase 2 work and getting, I think, rolling our sleeves up some more and actually getting into some of the actual testing and test methodologies now that we've worked through some of the beginning pieces. Anything from you, Suchen? If
Not really.
okay. How about you, Marco? Any last comments for you?
Well, maybe briefly from the conformal coding side.
Yeah, please. Yeah, talk about it.
The other project is also soon having the call for partners. It will be advertised equally, let's put it this way. Maybe the big difference between these two, if you consider the prevention of corrosion, comes back to corrosion of what. So here it was especially mentioned that corrosion and degradation of polymer is something which is known and challenging for the component, whereas in the conformal coating evaluation project, the main theme is to use the existing thin film serpentine pattern and to measure its corrosion and measure it electrically and measure the corrosion of the metal. So maybe these are the biggest differences, and of course the conformal coating project is in third phase already, so this is kind of mass producible module preparation and definition project.
I would say if you're interested in the project that Marco's talking about, or this phase 2 SOW work that's starting, or the study on the reused components, please email me, marcus@inemi.org. I put that in the chat window as well, and I will get you some more information or get you invited to those calls. I will say that the phase 2 activity right now is in what we call an initiative phase. So you do not need to be an iNEMI member to participate. So if you're interested, but you're not an iNEMI member and want to help talk about what is it that's important to you, that we can, incorporate into our SOW, if it lines up with what we're trying to do, we'd love to get some additional input there. The same is true for the reused components, or the, how do we call it here? Make sure I call it the right name. The study of use of recycled components, that also is open up to members and non-members right now, because we're in the early stages of what's important. So we're sort of in the scoping, not quite at SOW, but the early scoping work there. The conformal coding project that Marco talks about, that is unless I misunderstand, Mark, that is still, that's entering call participation, so that does require iNEMI membership. So
Yeah, but Mark, maybe I want to talk up a bit on this reuse components.
absolutely, go right ahead.
I mean, because like one of the points is we prefer to harvest from own products. I mean, instead of getting recycled components from a third party. Well, I mean, this is mainly to impose a proper review process. We managed to track the history of the used products and to avoid counterfeits as well. So the only question we have is how reliable is the harvested components. That's why this is part of the initial objective why we come up with this project. I mean, the main one is to avoid counterfeits. That's why we propose to, instead of getting the recycled components from third party, why don't we harvest from our own products, the unused products, scrap board.
Yeah, off lease or scrap. Yes, absolutely.
So yeah, let us know if you're interested to be part of the team.
Sure.
For this project.
Yep. We'll be talking more about both of these projects in the coming month. The phase 2 is in the newsletter for iNEMI that'll be coming out next week, so you can read a little bit more about it there. And once we have scoped this one a little bit more, we'll also be making, I think, an open call for participation in this study for the use of recycled components. And we've already heard a few things from you today, especially around counterfeits and sourcing of the materials that we need to be incorporating into our discussions. Anything else from anyone? Oh, not seeing anything. Thank you very much for your time and participation today. And Stephen and Suchan and Marco, thank you for joining us and speaking today. And we'll see some of you again later this evening in the US when we do this again. So thanks, and have a great day.
Good day.
Stephen. Bye.
Take care. Bye, everybody.